Computer Network Security Assignment Help. For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@computernetworkassignmenthelp.com, support@computernetworkassignmenthelp.com, or reach us at https://www.computernetworkassignmenthelp.com. Ben Bitdiddle is learning to code, and he has decided to build a website. To authenticate users, he created a database with all of his users' usernames and the SHA-256 hash of their passwords. Unfortunately for him, Eve has stolen the contents of this database. In this problem, we will explore some of the space/time trade-offs which Eve can use to invert cryptographic hashes of passwords. Suppose Eve knows that all the passwords come from a set S, and our hash function produces d-bit strings. With no precomputation, if S is much smaller than 2D, then inverting the hash of a password will take Eve about S/2 tries in expectation, and therefore time that is omega S. If Eve had infinite time to prepare for breaking the password hashes, she could construct a lookup table with the hash of every possible password in it. Inverting a password hash would just be an O1 table lookup, but Eve would then be required to store a table of size omega S. ComputerNetworkAssignmentHelp.com. Problem 1. Ben Bitdiddle is learning to code, and he has decided to build a website. To authenticate users, he created a database with all of his users' usernames and the SHA-256 hash of their passwords. Unfortunately for him, Eve has stolen the contents of this database. In this problem, we will explore some of the space/time trade-offs which Eve can use to invert cryptographic hashes of passwords. Suppose Eve knows that all the passwords come from a set S, and our hash function produces d-bit strings. With no precomputation, if S is much smaller than 2D, then inverting the hash of a password will take Eve about S/2 tries in expectation, and therefore time that is omega S. If Eve had infinite time to prepare for breaking the password hashes, she could construct a lookup table with the hash of every possible password in it. Inverting a password hash would just be an O1 table lookup, but Eve would then be required to store a table of size omega S. ComputerNetworkAssignmentHelp.com. Problem 2. The next idea is that F and H are alternately applied k times on a random password to yield a chain of k passwords and password hashes. Show that if we store a single entry in a lookup table mapping the last hash of this chain to the starting password, then in OK time, we can invert any of the hashes which occurred in the chain. Problem 3. A natural next idea is to store multiple hash-if password pairs in the lookup table, all constructed in the same way. Show that if all the corresponding chains are of length k, then we can efficiently invert the hash of any password which occurs in any of the chains. If you create S/k chains of length k as described above, do you expect the chains to contain close to S distinct passwords? ComputerNetworkAssignmentHelp.com. Problem 4. Rainbow tables use a different and independent pseudo-random function phi mapping 0, 1, d to s for each step of the chain. Why does this increase the number of distinct hashes you expect the chains to contain? Problem 5. How can Ben Bitdiddle modify his password storage scheme to make it infeasible for a pre-computed rainbow table to significantly weaken his users' passwords? ComputerNetworkAssignmentHelp.com. Solution 1. desire a pseudo-random mapping from 0, 1, 256 to S. First, we note that S is efficiently enumerable. In particular, S follows standard lexicographic order, where each of the 62 possible characters follows the ordering 0, 1a-z, a-z. Then, of the 6,210 possible values in S, the ith value is easily attainable by computing the base 62 representation of I-1. Now, we want a pseudo-random reduction function, R, which maps 2,256 possible values to 6210. One possible function is simply R, HV, equals SHA-256, HV, %6210. In other words, we use a hash function on the item from 0, 1, 256 to map to another item from 0, 1, 256 and then take the value mod 6210. This function is very nearly uniform, 2,256 since 6210 greater than or equal to 1059, assuming that the hash function is sufficiently random. Solution 2. The general idea is that given some hash HV, we can run it through a similar chain process k times. If any of the intermediate hashes match the last hash of some chain in Computer Network Assignment Help.com. The table, we obtain the corresponding start of the chain S. We start with S and walk through the chain again until we reach some segment hash PL equals HV, where PL is our desired plain text. Given that each iteration of hashing or reducing takes O1 time and that lookup takes O1 time, we have an OK algorithm for inverting any hash that occurs in some chain. Solution 3. We can use the scheme from before. The table can be represented as a hash table or sorted to allow for lookup via binary search. Then for every query hash HV, we repeat the process from part B, but lookups will take O, SK, or O1, depending on whether the table is implemented as a sorted list of entries or a hash table, respectively. In practice, this is not always true. First, HV might be part of a chain that shares an endpoint with another chain, but is not present in the table. Additionally, chains can merge on collision. A query might need to search through all such chains that share the endpoint before finding the chain that contains HV. One might guess that each chain may store K unique. Computer Network Assignment Help.com. Passwords, and that therefore K chains would store S distinct passwords. In practice, this is not true. Given K chains of length K, the number of distinct passwords will be much lower than S with high probability. The issue is the presence of collisions. For example, let's consider the ES optimistic situation where the first 4 K chains all contained completely unique passwords. In other words, 1/4 of the password space has been successfully encoded without collision. Now, we want to lower bound the expected number of lost passwords. Consider the remaining 3/4 SK equals T rows. For each row, we analyze the probability that one of the first K2 elements in chain I collides with some element in the first half of a previous chain. In particular, if some collision occurs in the first half of chain I with an element in the first half of a pre-existing chain, then at least K2 passwords in chain I are lost by merging. It's easy to see this as a lower bound on the losses, since this case only represents a subset of the cases where passwords are lost. Lost passwords in chain I, greater than or equal to K2PR, element in first half of chain I collides with element in the first half of existing chain. Computer Network Assignment Help.com.